I think lecture number 9 is a great place to stop for a moment, take a look at what we've already done in this course and where we're going in this course. In developing our understanding of finite element methods, we are more or less going in the same order that these methods were themselves developed. So far, we've looked at the direct method. Now, the direct method is based on Hooke's law. It's fairly straightforward to understand, and it's useful for analyzing systems of springs and trusses. But the method itself doesn't lend itself to being extended to solving a wider variety of problems involving a wider variety of differential equations and a wider variety of physical systems that were modeled by those differential equations. So later researchers looked at something called the principle of minimum potential energy. And using this principle of minimum potential energy, they were able to develop a set of methods that, when applied to systems of springs and trusses, resulted in the same set of linear algebra equations as the direct method. But they could also use their method for developing solutions to problems involving objects that are deforming as long as that deformation is elastic. Other researchers looked at a concept called virtual work. And looking at virtual work, they were able to develop methods that, when applied to systems of springs and trusses, resulted in the same set of linear algebra equations as the direct method. And when applied to objects that are deforming elastically, they resulted in the same set of linear algebra equations as the methods based on the principle of minimum potential energy. But using their methods, they were able to solve problems involving any deformation of objects, whether or not that object is deforming elastically or not. It wasn't until the 1960s and the 1970s that people started developing methods based purely on the mathematics of differential equations and a type of mathematics called variational calculus. Because these methods were based purely on the mathematics of the differential equations themselves, it opened up finite element analysis to be used on a much wider variety of problems, such as problems involving heat transfer, fluid flow, changes in electrical potential, and so forth. So we've already looked at the direct method, and in the next few lectures, we're going to start developing methods based on this principle of minimum potential energy. Since in this class, when looking at deforming objects, we're going to restrict ourselves to looking at elastic deformation, we're not going to study the virtual work methods in this class. However, in the next few weeks, we will start developing a method called the Glurkin's method, which is one of these methods based purely on the mathematics of differential equations and variational calculus. In the next video, I'm going to start laying out the strategy we will use for developing this method based on the principle of minimum potential energy.